So far, we've been concentrating on making inferences about one population mean. But there are many other situations where you would like to make an inference involving a parameter that exists in the population. We are next going to talk about the situation where we have two different populations, two different population means, and we would like to compare them by making inferences. In particular, we're going to actually subtract the two means from each other to do this comparison. So here's our diagram that we've been looking at all semester, but now modified for our present situation. So again, we have two different populations. Each has a population mean. Population 1's mean is mu1. Population 2 means is denoted as mu sub 2. And to make the comparison between the two, we simply subtract mu1 minus mu2. Now notice that if this is equal to 0, that means these population means are the same. If it's not equal to 0, that means, of course, that they're different. And that's the situation that we will typically concentrate on here. Again, these populations might be difficult to get at in terms of the individual items in the population. So we take a representative sample from each population so that we have a more manageable set of data to look at. These samples are taken in a way so that they are independent of one another, meaning what I get from population 1 is not dependent upon what I get from population number 2, and vice versa. In the sample, then, we calculate the corresponding set of statistics. Y bar 1, sample mean from sample number 1. Y bar 2, sample mean from sample number 2. We subtract the two so that we can make comparisons. Then, as we've done before, using what we obtained from this sample, this set of information that's more manageable to work with, we then make inferences back to the population itself. Now, where would something like this be of interest to compare two population means? Well, there are lots and lots and lots of examples. Simply, if we think in terms of a university environment, who receives higher grades on average? Let's say athletes or non-athletes. But in the pharmaceutical industry, in terms of, let's say, comparing two pharmaceutical products, or in the development of a new pharmaceutical product, very often you're comparing, let's say, the mean response for one to another. So one in particular that I've seen done before is in terms of which allergy medicine, Claritin or Allegra, relieves allergy symptoms the best on average. Other situations would be, let's say, an economist wishes to determine whether there is a difference in mean family income for households in two socioeconomic groups. How can we do that? Well, let's take some samples from these two different populations, one could say, and then do inferences. So what you're going to see next then is some very similar development to what we had for a confidence interval for one mean, and also a hypothesis test for one population mean. Very, very similar development. That's why we spent a lot of time on those sections, making sure you understood how these items were developed, and so that you could get an intuitive feel for what the confidence interval will be in terms of, let's say, its width or its location. Also in terms of hypothesis tests, so that you understand, let's say, the effect of the sample size on a hypothesis test, or understand, well, there's a wide variety of different items. We can now apply those tools that we've learned there to now essentially a slightly different situation. Okay, so you hopefully will remember that we talked about a central limit theorem when we were with respect to one sample mean. Well, there's many different versions of this central limit theorem for other statistics of interest. So for example, with respect to two sample means, let's say we have samples of size n1 that comes from population number 1, sample of size n2 that comes from population number 2. We're interested in mu1 and mu2. We also have corresponding variances for each of the populations, sigma 1 squared and sigma 2 squared. And if we look at the difference in the sample means, these two statistics then, one could actually show, and you would do this in like a mathematical statistics course, that what I would expect on average this difference to be, fortunately, is mu1 minus mu2. So that's good. In a mathematical statistics course as well, you would look at deriving the variance now of y bar 1 minus y bar 2, and that's equal to the variances divided by their corresponding sample sizes, and then you add them up. This y bar 1 minus y bar 2 has an approximate normal probability distribution corresponding to the central limit theorem. Sorry if I didn't say that before. Since it has this particular distribution, what one could do is form a standard normal random variable with this using the same techniques that we did before. So just as a reminder, this is what we worked with before. That had a approximate normal distribution. Now we just replace where we saw y bar with y bar 1 minus y bar 2 and make other corresponding replacements as well. And we get this new quantity z that has a standard normal distribution approximately for large samples. Well, what does large samples mean? Well, similar to what we've seen before, that generally speaking, a sample size of 30. Now for each sample, will allow the central limit theorem to work. We can then find probabilities in this situation just like what we did in the past. So how can we then use this result like we did in the past to find a confidence interval now for mu1 minus mu2? Well, back in the past, we looked at a quantity such as this. Where this z was y bar minus mu over the square root of sigma squared divided by n. We can do essentially the exact same thing here. Again, we make just the corresponding substitutions. And so what we have then is in this probability, because we're dealing with random variables, y bar 1, y bar 2, we can talk about probabilities. This probability, when you choose the corresponding quantiles from a standard normal, has an approximate probability of 1 minus alpha. Then one can do some algebra to rearrange quantities in this probability and look at this. Look what's in the middle, mu1 minus mu2. So then this allows us then to replace then the corresponding random variables with their observed values. In other words, the lowercase letters, so that we can actually state a confidence interval, 1 minus alpha times 100% confidence interval for mu1 minus mu2. But again, similar to before, we have some problems. And we have these unknown variances, unfortunately, for the population. So in the end, we can't actually use this expression for a confidence interval. So what do we do? Well, there are a few options. Let's talk about the first option here. In the end, we won't use this particular option, but I do want to mention it because you will see sometimes people use this. Let's say we can assume that these population means are equal to one another. This might make sense in some situations to do that. If, let's say, population 1 has a lot of similar characteristics to what you have for population number 2. And if you do that, then now you only have one parameter that you have to worry about, let's say sigma squared. And so what you can do then is estimate it with what's called a pooled variance estimator. And when one does that, then one can now, similar to what we did before in the past, work with a t-distribution and derive a corresponding confidence interval. And this is what the confidence interval looks like. Again, we have our statistic, y bar 1 minus y bar 2, or the difference of the two statistics. Then we have the quantile from a t-distribution. And notice the degrees of freedom here. That's n1 plus n2 minus 2, which will be, let's say, equivalent to n1 minus 1 plus n2 minus 1. Remember, when we only had one population mean, we had n minus 1. So now you can see where this degrees of freedom comes from here. Then now we have then this pooled estimator of, in this case, the standard deviation. And then we have the square root of 1 over n1 plus 1 over n2. On the right-hand side, you have exactly the same thing, but now you have a plus. Well, what is this pooled estimate of the variance? What's this quantity here? And for you to have some general understanding of where this comes from, what you could do is actually write it out in terms of what would be a sample variance if it came from sample 1. What would be the sample variance if it came from sample 2? You're going to see some things cross out, and then it will make sense more how this quantity comes about. But we will not use this expression either because in some situations, yeah, the variance will be equal, but in other situations it may not. So let's be more general, and we're going to go with option number 2 here. Okay. So what we can do is, again, come up with the sample variance from sample 1. Come up with the sample variance for sample 2, where we don't have this equality assumption, and we can work with that to come up with a confidence interval. Okay. So, to start off with, we have this quantity t, as we saw, a while ago, with respect to one population mean. And now we just write it out in terms of y bar 1 minus y bar 2, mu 1 minus mu 2, and then take a look at what we have here. Here's our measure of the variance for y bar 1 minus y bar 2. Notice where the capital letters are. Those are the random variables. This quantity, this capital T here, has an approximate T distribution where the actual corresponding degrees of freedom is this guy right there. This is the Greek letter again, nu, as in nu. This is kind of a complicated expression there. Don't worry about the actual derivation of where this degrees of freedom comes from. If you are interested, this is referred to as a Satterthwaite adjustment, named after the person who came up with it. It's a common adjustment or common way to come up with degrees of freedom in situations like this. Again, in a mathematical statistics course, that's where you would talk about the derivation. You've heard me talk about mathematical statistics courses a lot. Hopefully, this class that we're taking here will make you say, maybe I want to take a mathematical statistics course. That looks like it would be fun. Then again, maybe you won't feel that way. Still, if you take an experimental design course, which is often a follow-up course to the course that we're doing right here, you'll use Satterthwaite adjustments a lot. Now, with this messy expression, as you might expect, since we have these sample variances in there, we're doing divisions, we're doing multiplications. As you might expect, this degrees of freedom might not be an integer. In the past, we've only seen situations where like a degrees of freedom might be 5, 30, 99, something like that. Now it could be, let's say, 30.4. So it's not necessarily an integer. And that's okay. There's nothing wrong with that. But I do want to point that out too, so you're not alarmed by this. And also I want to point it out is that because many books will unfortunately take an old approach with dealing with a situation like this with the degrees of freedom that's not an integer, and they'll say, okay, instead of using, let's say, 30.6, use just 30 instead. But there's no need for doing that. R is going to have no problems doing our calculation with a degrees of freedom that's a non-integer. Okay, so since our quantity here, t, is a random variable, because of that, we can find appropriate quantiles from our t distribution, put them on either side of this capital T, and we now know a probability then associated with this quantity. And it's approximately 1 minus alpha. just like what we saw for a confidence interval for one mean. With that then, we can then finally get to a point where we get to the confidence interval that we're going to use. So again, we start off with y bar 1 minus y bar 2, the observed values. We subtract off our quantile from the t distribution with new degrees of freedom. And then we take it times then the square root of sample variance from sample number 1 divided by its corresponding sample size, plus do the same thing then with the sample number 2. That's our lower bound. The upper bound is exactly the same, but now we put a plus sign in there instead. Okay? So let's take a look at an example where we can actually put this to use. This deals with this dividend yield data set that we've seen previously. And we might be interested in answering the following question. Is there a difference in average dividend yield of companies traded on the NASDAQ versus the New York Stock Exchange? Going into this particular question and coming up with this idea to do this investigation, I thought, probably the New York Stock Exchange would have companies with higher dividends, because typically companies that are traded on that stock exchange are, let's say, more well-established, larger companies. But that's not always necessarily the case, especially nowadays, because a lot of large tech companies are traded on the NASDAQ instead. But I was, interested in taking a look at that, see if maybe my research hypothesis was true. So, to help do this, let's find a 95% confidence interval to estimate the mean difference. So we're going to let 1 be NASDAQ. New York Stock Exchange is going to be 2, and we're going to look at mu1 minus mu2. So to do this, I actually took a random sample of 30 stocks that were traded on the New York Stock Exchange and 30 stocks that were traded on the NASDAQ. For each stock, for the day that I did this sample, I recorded its closing price. So for this particular stock, it was $25.25. I recorded the annual dividend, $1.90 per share. And then to get the dividend yield, I took 1.9 divided by 25.25. Here are some plots and numerical summaries of the data. So what we can see here is that we got kind of a weird looking shape of our sample in terms of the samples distribution itself of these dividend yields. So notice how we have a lot of zeros down there. And then what I kind of expected is that, there's going to be like a number of well-established companies that will have a higher dividend yield. But I have to admit, after taking the sample, I didn't have as many as I expected. And notice how we have this clump of dividend yields down here for the NASDAQ, but we do have some outliers as well. We can also take a look at histograms comparing these two situations. Now, do note when you do these histograms, it's important to put these on exactly the same scales so you can make comparisons from above to below. Now, on your own, you should think about, what are these right skewed or left skewed? If you don't know what the answer is, please ask. But we definitely see that these are not symmetric distributions at all. So when we read in our data, this is what the data looks like. We will concentrate on this dividend yield column. We'll also concentrate on the exchange itself. So if we did some summary measures, so I use the aggregate functions we've done many times before, and I'm going to use the mean function with that. We can see that, at least in terms of the sample mean itself, definitely the New York Stock Exchange has a higher dividend yield than the NASDAQ. Here are the sample variances. Notice that, or sample standard deviations, excuse me. Notice these are very quite similar. And then also we can look at, let's say, some quantiles as well. So the 0.75 quantile for the two, we can see New York Stock Exchange is much higher. But take a look at this. The medians are both 0. So again, quite a weird looking distribution for the sample. So questions. Do you think there's any preliminary evidence of difference between the mean dividend yields for all the companies traded in the New York on the stock exchanges? Well, we can definitely see in terms of the sample means some differences. But if we take a look at this box and dot plot, we do see this kind of a shift up of points in comparison to the NASDAQ. But still, we get all these zeros down there. So, I do see some evidence, but, at least from the sample, in initial look, it doesn't necessarily appear to be strong evidence. What do you think about the normality probability distribution approximation for each population? Well, I think we're going to have a problem with that. We have these skewed distributions here. Is the normal probability distribution approximation for each population needed, though? Well, again, based upon what we've learned before in terms of like the central limit theorem, based upon what we've learned before about these, like a confidence interval for one mean with a normal distribution, when we're dealing with sample sizes are large enough, based upon that information there, in the end, this shouldn't be necessarily a big deal to have this non-normality in our data. So let me actually go on over here to R, or 10 first, and let's do some further calculations. So I'm finding a 95% interval, so we're going to set alpha to be 0.05. And then I'm going to take the results from aggregate. I'm going to put that into an object called sample.mean. Okay, let's take a look at what's inside of save.mean. It's actually a data frame, and of course I could do save.mean with it, or I'm sorry, name save.mean. And so if I did save.mean $ dividend yield, look at how I can pull out those dividend yields. So the first element is for NASDAQ. The second element is for the New York Stock Exchange. So let's pull those out and put them into objects called y bar 1 and y bar 2. Okay. We're going to do exactly the same thing with the sample variances. And we're also going to do the same thing with the sample sizes. To do the sample sizes, notice that what function I use? Length. Okay, so N1 should be 30. In fact, it is. Okay, let's do some more calculations. First of all here, let's do that degrees of freedom, that messy looking formula that we saw there, and simply I just put it into the correct syntax corresponding to R. It is kind of messy, so to make sure that you get it right, what you could do is just highlight segments of the code, check what it looks like when you actually run it, and that will help you see that indeed that you are getting everything right. So we're going to find new, and let's put all our results in a nice little data frame so that we can print it off. So notice our degrees of freedom here is 57.46. The quantile from our t-distribution that we're going to need is 2.002. How did I find that? Again, well, in the data frame here, I used the qt function to find what I needed. Then it's just a matter of finding that lower and upper bound. Y bar 1 minus y bar 2. Subtract off the value from the t-distribution. Take it times the square root now of s1 squared divided by n1 plus s2 squared divided by n2. So let me go ahead and do that. Put it on a data.frame, and there's our confidence interval. Negative 0.02453 to positive 0.0069. Okay, let's jump back over here to Word. So let's see, on the bottom of page 12, I actually went through the calculations so that in terms of writing everything out so you can see how all the components come together. Here's our confidence interval as well. So one possible interpretation would be I am 95% confident that the difference in dividend yields between the NASDAQ and New York Stock Exchange is between negative 2.45% and 0.7%. Another way to phrase this is that in 95% of similarly constructed intervals, I would expect the true mean difference or the population mean difference between these two stock exchanges in terms of their dividend yields. I would expect that difference to be within 95% of all these intervals. Now, one thing that you always have to be careful about when you do something like this in an interval, you need to make sure it's clear what the 1 and the 2 represents. So one way to avoid that problem is you could put mu NASDAQ minus mu New York Stock Exchange. So a little bit less formal, but at least it's more descriptive. So that's another way that you can write it out. But another reason why you need to remember what 1 and 2 is, because then you're wondering, well, especially if the interval, let's say, was negative 0.5 is less than mu1, negative 0.05. Mu1 minus mu2 is less than negative 0.01. So notice how that entire interval now is less than 0. And if you looked at an interval like that, you might be wondering, okay, now which one is greater than? Because notice 0 is not in the interval. And you got to keep track of, well, what was 1, what was 2, so that you remember which one is greater. So then I guess that leads to, well, an eventual question that I'll ask, and that is, okay, well, based upon these samples, can we make any conclusions about if one stock exchange has a higher dividend yield on average versus another? And the answer is no, because notice that 0 is inside this interval. And again, the reason why that would be important to know is that if mu1 minus mu2 is equal to 0, that means, let me do some erasing, oops, just to make sure this is clear. This would mean then that mu1 is equal to mu2. And so since 0 is in that interval, well, they could be equal indeed. So we cannot say that one is larger than the other in terms of these mean dividend yields. Okay, let me go back here to 10. So I showed you the harder way to do the confidence interval first, because it's very important to understand how these calculations are being done. An easier way would be simply to use the function called t.test, where the syntax then is as follows. We use now an argument called formula. It's equal to, well, what are we interested in? We're interested in the dividend yields, and we're interested in these dividend yields by exchange. We've seen similar syntax like this when we've used the aggregate function. Our data is in a data frame, happens to be called div. And then we need to say, well, are we going to assume that the population variances are equal or not? And if you remember, we don't. So we put a false there. And then we can put what our confidence level that we're going to be working with is for the intervals. And then later on, you'll see when we do a hypothesis test, we typically will want to do a difference we'll typically look at a null hypothesis value of 0. So that's why you see mu equals 0 there. More about that shortly. And so I'm going to highlight that code and run it. And here we go. Here's the exact same interval that we just calculated. Okay. So questions. We've already addressed this first question essentially. Second question, what are the populations? That's a little bit of a tough question here. Obviously, I took my samples from both exchanges, but we know that these dividend yields, then the corresponding prices for these stocks change from day to day to day. So what are my populations? Well, the populations were all stocks that were traded on the exchanges on this particular day that I took my sample. Ideally, though, we would like to be able to extend these populations to mean let's say, all stocks traded on these exchanges for let's say, now and into the future. And generally speaking, if, let's say, economic conditions don't change, if the way the structure of our economy doesn't change, that's usually a safe thing to do. But, over time, these changes do occur. And so to some respect, then, our populations are probably stocks on these stock exchanges within a much shorter period of time corresponding to when that sample was taken. Now, what would you expect the plots to look like if there was enough evidence to indicate a difference between the means? And so let's talk about that. I'm going to bring up a software package called Windows Journal. So we've seen what the dot plots look like already. I'm going to draw another set of dot plots here. Okay, let's actually go back to what those dot plots were originally. Here we go. Let's see. Let me do some erasing. So it's unfortunate too. What is complicating things is all these zeros that we have down there. But what we're looking for is a situation where there is separation between let's say the y values, just to be more general, separation between the y values for one of the samples versus another sample. And we saw some separation here, but we also saw some overlap, especially down low. And so that was why I was kind of hesitant to say, yeah, the samples are telling me that it looks like there could be evidence that there's a difference in the population means as well. But let's look at a different setting. Now, if I had, and this is just in general, so let's say I have just a y there. And actually, let's make this, let's say, a 1 and a 2. So we're not necessarily talking about dividend yields anymore. If I saw something like this for my samples, so these are supposed to be dots that you would have on a dot plot, we see definitely the two samples are separated in terms of the y values. I could draw a line here that shows indeed they are separated. When I see something like this, before I actually did a confidence interval, I would think, oh, I bet then that mu2 is going to be larger than mu1. Or at least I wouldn't be surprised if that's what our conclusion was. A lot of this is also dependent upon the variability in our sampled values too. But then let's say now we're starting to get some overlap. Now we definitely have a shift. 2 is shifted higher compared to 1. 1 tends to be below, but we do see some overlap. Even in that situation, and again, it's dependent upon the variance too, I would start thinking, yeah, I wouldn't be surprised if mu2 is greater than mu1, based upon this information that I received in my sample. It looks like there's some differences. Now let's keep on going here. So again, we see the sample 2 is shifted a little bit higher compared to sample 1. This might make me think, yeah, I do see that shift there, but I won't be surprised because there's so much overlap that we can't, from these samples, conclude that the sample means, that the population means are different. Then if I see something like this, now we see these two situations where both samples have a large amount of overlap. In fact, they're almost like, I guess, completely overlap. In this situation, I would say, yeah, I'm probably not going to find a difference in the population means. So with this little demonstration here, I want you to always have this in the back of your mind, and we'll see some other examples of this later in the semester. I want you to always have this in the back of your mind of a way to intuitively understand what a confidence interval will give us, and then also, as you will see shortly, what a hypothesis test will give us when we look at the differences between parameters from two different populations. We are always looking for stuff like this. And that's one of the reasons why I really like dot plots. I really like box plots to help you see what a confidence interval and what a hypothesis test will actually conclude. Okay, so what about hypothesis testing? Well, we can do it just like what we did before. Now we just make those same corresponding changes. So with respect to the confidence interval method for a hypothesis test, then we simply state our hypotheses, and we will always, well, I'm pretty sure that in our class we will always look for mu1 minus mu2. We'll always do that comparison with respect to 0. There's very little situations, and to be honest, I can't think of any off the top of my head where you would want to do something other than 0 there. We have a two-tailed test here, but one could also write this in terms of a one-tailed test. If you remember what my original research hypothesis was that the mean for New York Stock Exchange would be higher than the mean for NASDAQ. I would put then that research hypothesis into HA if I was interested in doing that. I decided for this particular example here to look at a two-tailed test. Okay, so then we state our confidence interval. Notice that 0 is inside the confidence interval, so therefore do not reject HO. And lastly, well, what does this mean in terms of the original problem? There is not sufficient evidence to indicate a difference between the mean dividend yields for companies traded on the two stock exchanges. Well, what about using now a test statistic or a p-value? We can do that too. We saw earlier this statement, this probability statement relative to a random variable t that contained our necessary information that was used to come up with our confidence interval. Well, rather than going through all those algebraic steps, how about we just simply use the sample version of this quantity that's inside this inequality then as our test statistic. So then our test statistic then will be t, and we can write it out in terms of the sample quantities or the observed quantities there. So turn the uppercase letters into lowercase letters. On your own, make sure you can answer this question. If you can't, then you need to actually ask a question via message board or through other means that we have available to contact me. So the question is, well, what are the critical values for two-tail, left tail, and right tail tests? It just simply follows from what we had when we only had one population mean. We can also calculate a p-value for a two-tail test, just like what we did before. 2 times the probability of random variable t is greater than the absolute value of the observed test statistic value. Again, on your own, think about what the p-value would be for a left and right tail test. You do definitely need to know that. Okay, so let's go back to the dividend yield example. If you remember, we looked at this t.test function before. The key thing is this part right here. If I want to do a test where in HO we have some kind of equality sign here, and we're checking it with, we're comparing it to 0, then I say mu equals 0. Now, obviously, we're dealing with 2 different population means here, but this is just the syntax in t.test, and so that's why we say mu equals 0. Note that there are corresponding arguments in t.test that allow you to do a one-sided or one-tailed test as well. The default is two-sided. So this is what we get then. Here's my t-test statistic or observed test statistic value. Here's the corresponding p-value as well. Again, I just want to emphasize var.equal false there. So let's formally do the hypothesis test then. Test statistic method, let's state HO and HA. Step 2, we calculate the actual test statistic, negative 1.12. We find the quantile from a t distribution using the QT function, as we've done many times before. Notice this degrees of freedom there, 57.45. Step 4, we plot everything out. And we can see our test statistic falls in our don't reject region. Here's a critical value. Here's a critical value. So we actually need to state then the following. Do not reject HO because -2 is less than -1.12 is less than 2. We actually need to state that. Step 5, what does this mean in terms of the original problem? Well, same as before. There is not sufficient evidence to indicate a difference between the mean dividend yields. In terms of the p-value method, look how we're going to actually calculate that. Again, a p-value measures how extreme is a test statistic relative to the t-distribution. So if we look at then this area underneath the curve, that gives us our measure of extremeness. That's the probability that t is less than -1.12, or equivalently, the probability that t is greater than the absolute value of -1.12 using the symmetry property of the t-distribution. To find our p-value, we actually multiply this probability by 2 because, again, we have rejection regions on both sides of our probability distribution. So using the PT function, you could find this corresponding probability. We state our alpha using 0.05, and then we actually need to say this, do not reject HO because 0.2682 is greater than 0.05. Conclusion is the same. Okay. Now, a few things here. Let's see here. If we want to, we could actually save the results from t.test into an object. Let's call it save.test for a lack of a better name. And then save.test is actually a list type of object using R's terminology. So with that, we can use the names function with it, and we can see how we can get at certain values inside this object. In particular, save.test $statistic is our test statistic that we calculated before. Let me come back here. Now, let's say if we did go with what my research hypothesis was, where we did a one-tailed test. In that particular situation, then, and I guess I already kind of said this before, now we can state a particular alternative in terms of what directions our inequality sign is going. Here I have less. And if I go through the results, test statistic remains the same, but the p-value is adjusted. It's 0.1341. Again, don't reject HO. Notice how the confidence interval is found as well. It's a one-sided confidence interval, as we've seen in other applications. Okay. Let me just make sure I talked about everything that I wanted to here. Let me look at my notes. Yes, I did. So that concludes then the discussion about how to do a hypothesis test for the difference of two population means, where how the samples are taken from these two different populations are taken in an independent manner, meaning how you obtain one sample is not related on how you obtained a second, the sample from the second population. So that concludes this set of notes then.